3 tropical cyclones, spinning up almost simultaneously in the same corner of the Pacific near Papua New Guinea, months before anyone expected the ocean beneath them to do anything unusual at all. According to reporting from the Washington Post, that triple cyclone cluster is what actually helped kick off the specific atmospheric event now driving one of the most powerful El Niño events scientists have ever tracked in the modern instrumental record. For weeks, forecasters knew something big was building in the tropical Pacific. What they didn't fully understand, until researchers started digging into exactly what triggered it, was why this particular event accelerated so much faster and grew so much stronger than anyone initially expected. Let's break down exactly what scientists found, why this specific mechanism matters so much, and what it means for the historically significant El Niño now taking shape. Subscribe to the channel before we get into this, because I track exactly this kind of major, rapidly evolving climate story with the real science behind it, not just the scary headline summary. Let's start with the actual scale of what's forming, because the numbers here are genuinely extraordinary. NOAA's Climate Prediction Center confirmed El Niño conditions had officially developed as of early June this year, with waters in the eastern and central Pacific near the equator warming to more than 0.5 degrees Celsius above average, the formal threshold marking the transition out of the La Niña that had been in place since the prior summer. By the most recent Climate Prediction Center discussion, the Niño 3.4 index, the specific patch of ocean scientists watch most closely to track this cycle's strength, had climbed to plus 1.2 degrees Celsius. NOAA's own modeling gives this event a 97% probability of persisting into early spring 2027 and an 80% probability of reaching very strong intensity specifically during the October through December window, a threshold defined scientifically as sea surface temperature anomalies in the benchmark region exceeding and sustaining plus 2.0 degrees Celsius or higher above the long-term average. That would place this event among the strongest ever recorded, potentially rivaling or exceeding the historic 1997-98 Super El Niño, widely considered the most powerful event of the entire 20th century. Now let's get to the actual question this video is built around, because understanding why this specific event grew this fast and this strong is genuinely one of the more fascinating pieces of atmospheric detective work happening in climate science right now. Paul Roundy, a professor at the University at Albany and a leading El Niño researcher, has been tracking the specific mechanism behind this event's rapid intensification, and his explanation gets directly at the heart of what's actually driving this. This year, Roundy explained, a series of extraordinarily powerful westerly wind bursts over the Pacific pushed a vast reservoir of accumulated water eastward toward the equator. That's the actual engine behind this entire event. And understanding exactly what a westerly wind burst is and why this year's version of it turned out to be so unusually powerful is genuinely the key to this whole story. Let's talk about the basic mechanics first, because you need to understand the normal state of the tropical Pacific before you can appreciate how dramatically this year's westerly wind bursts disrupted it. Under ordinary conditions, persistent easterly trade winds blow steadily from east to west across the tropical Pacific, piling up warm surface water against Indonesia and the western Pacific, while allowing cooler water to well up along the coast of South America in its place. A westerly wind burst is essentially a sudden, temporary reversal of that pattern, a surge of wind blowing the opposite direction from west to east, typically lasting anywhere from several days to a few weeks. These bursts act like a genuine physical shove, pushing that accumulated pool of warm water directly eastward across the Pacific. And critically, they generate what oceanographers call downwelling Kelvin waves, subsurface pulses of warm water that propagate eastward beneath the ocean's surface, along the boundary separating warm surface water from the colder water below. As those Kelvin waves travel across the Pacific over a period of weeks to months, they eventually reach the eastern Pacific and rise toward the surface, releasing their accumulated warmth and driving the surface warming that officially defines an El Niño event. Here's where Roundy's research becomes genuinely specific and genuinely significant. Because he didn't just identify that westerly wind bursts were happening, he found a direct, quantifiable historical parallel that explains exactly why this year's event has so much momentum behind it. The closest parallel, Roundy explained, is a wind event in early 1997, which preceded what was probably the strongest El Niño of the entire 20th century. And this year's version of that same mechanism has actually outpaced its 1997 predecessor in a genuinely measurable way. The warm water to the east of this year's westerly wind burst is about half a degree warmer than the warm water was at the same point in 1997, Roundy said. It has basically been hit with all the momentum that is needed to bring the event over the intensity of what was achieved then. That's a genuinely remarkable, specific scientific finding, not a vague, hand-wavy comparison to a historically significant event, but a direct quantified measurement showing this year's underlying warm water anomaly running warmer than the exact event most scientists consider the benchmark for extreme El Niño intensity. I want to walk through the actual statistical case Roundy built around this finding because it's genuinely one of the more confident statements you'll hear from a climate scientist about a forecast this far in advance. Based on the distributions of historical surges in the trade winds, the distribution of westerly wind events, and how strong the recent event has been, Roundy explained, it would take an event well beyond the 99th percentile in intense trade winds to render the developing El Niño event just strong and not extremely strong. Translate that into plain language, and it means the westerly wind bursts driving this year's event have already been so powerful that only an extraordinarily unlikely, statistically rare countervailing shift in the trade winds, something in the most extreme 1% of historical variability, could now prevent this event from reaching the very strongest category scientists track. In other words, a very strong El Niño is now close to certain. Whether it actually breaks all-time records remains a genuinely open question, but the underlying intensity threshold has essentially already been locked in by the specific strength of the wind event that triggered it. Now let's get to the detail that I think genuinely earns this story its "scientists just realized why" framing, because it's specific, it's traceable, and it's the kind of finding that only emerges once researchers go back and carefully examine exactly what was happening in the atmosphere at the moment this entire sequence began. According to reporting from the Washington Post, 3 separate tropical cyclones formed nearly simultaneously near Papua New Guinea, and that unusual clustering of storms is specifically what helped drive the westerly winds responsible for kicking off this entire event. I want to explain why 3 cyclones forming together in this specific way can actually influence something as large-scale as an ENSO transition, because it's a genuinely elegant piece of atmospheric physics once you understand the mechanism. Tropical cyclones are themselves low-pressure systems, and the air circulating around and between multiple simultaneous cyclones positioned near each other can reinforce and organize into exactly the kind of coordinated large-scale westerly wind surge capable of producing a genuine westerly windburst event, rather than the more common, weaker, disorganized wind fluctuations that don't carry enough sustained force to meaningfully disturb the broader Pacific circulation. When you get 3 storms forming together in close proximity, near enough to interact with the same broader wind field, you get exactly the kind of amplified, coordinated atmospheric shove capable of producing a westerly wind burst as unusually powerful as the one Roundy and other researchers have been tracking this year. Let's talk about how researchers actually confirmed just how historically unusual this specific wind event turned out to be, because the analysis behind it genuinely deserves real attention. Using ERA5 reanalysis data, a comprehensive, continuously updated dataset combining decades of historical weather observations with modern modeling techniques to reconstruct atmospheric conditions going back generations, researchers calculated a zonal wind ranking for June and July of this year, comparing the strength of westerly wind anomalies across the tropical Pacific against the full historical record stretching back 86 years. What they found was genuinely remarkable. A broad region of the western and central equatorial Pacific recorded its strongest low-level westerly wind anomalies on record during that specific window, with the surrounding areas ranking among the top 5 strongest observed across that entire 86-year comparison period. That's not a subjective, qualitative assessment that this year's wind burst felt unusually strong. It's a direct, quantified statistical ranking placing this specific event at or extremely near the top of an 86-year historical record. I want to explain why researchers needed to develop specialized tools just to properly track this event as it unfolded, because it genuinely illustrates how seriously the scientific community has been treating this specific development. Watching El Niño unfold in real time isn't as straightforward as it might sound, even with modern satellite technology. Hundreds of floats and buoys continuously monitor winds and water temperatures across the Pacific, but they're spread across an ocean larger than all of Earth's land masses combined, meaning genuine gaps in coverage remain even with this extensive monitoring network. Compounding that challenge, the rising baseline temperature of the oceans due to long-term global warming makes it genuinely harder to cleanly distinguish El Niño's specific signal from the broader warming trend, simply raising ocean temperatures across the board, year after year, regardless of the ENSO cycle's current phase. To address exactly this problem, researchers have increasingly relied on a metric called the Relative Oceanic Niño Index, or RONI, specifically designed to help that El Niño-specific signal stand out clearly from the steadily rising background warming trend, essentially correcting for the fact that an ordinary El Niño event occurring today registers as measurably warmer in raw terms than an equally intense event would have registered several decades ago, simply because the entire ocean has warmed considerably in the intervening years. let's talk about the actual sequence of events in more detail, because understanding the full month-by-month timeline genuinely helps illustrate just how fast this specific transition unfolded once it actually began. The La Niña that had persisted through the prior year began collapsing following a westerly wind. Burst that started in January of this year, with subsurface ocean anomalies confirming the transition toward El Niño, was already underway. As that same broader mechanism continued through the spring, an early April westerly wind burst was specifically identified as one of the strongest observed in at least several decades. And researchers were already noting at that point that the next substantial westerly wind event would likely occur during the final 10 days of May. Forecasts that proved directly relevant to the subsequent acceleration this event went on to demonstrate. By June, NOAA had formally confirmed El Niño conditions had developed. By July, the zonal wind ranking analysis was confirming this event's wind bursts as among the strongest ever recorded across an 86-year comparison window. And by the most recent updates, forecasters were describing this event using language reserved for only the rarest, most historically significant occurrences of this climate cycle, with Niño 3.4 index measurements climbing past 1.2 degrees Celsius and continued strengthening expected as we move through the fall. I want to explain the underlying physical reason why these subsurface Kelvin waves, triggered by the westerly wind bursts, are so genuinely important to how strong this event ultimately becomes, because it's the mechanism connecting the wind event itself to the eventual sustained strength of the El Niño it produces. While the westerly wind burst functions as the initial engine, the true power of a forming El Niño ultimately comes from the large, subsurface warm anomalies it generates, tracked specifically through a measurement called ocean heat content, which examines temperature down to roughly 300 meters, about 1,000 feet beneath the surface. As the warm water carried eastward by this year's exceptionally powerful wind bursts continues rising toward the surface, it provides a continuous, sustained supply of thermal energy capable of keeping this El Niño event strong and healthy well into the winter season, rather than producing only a brief temporary surface warming that fades quickly once the initial wind event itself has passed. That's genuinely the mechanism explaining why researchers are so confident this event will persist with real strength through the coming months, rather than simply representing a short-lived spike that could fade before winter fully arrives. Let's talk about why this specific event accelerated so much faster than forecasters originally expected back in the spring, because understanding that acceleration mechanism connects directly to the broader physics of how El Niño events actually intensify once they begin developing. Once triggered, an El Niño event can become genuinely self-reinforcing through a process called the Bjerknes feedback, named after the meteorologist who first documented this mechanism. As warm water shifts eastward and trade winds weaken in response, that weakening itself further reduces the upwelling of cold water along the South American coast, which warms the eastern Pacific even further, which in turn weakens the trade winds even more, creating a positive feedback loop capable of rapidly amplifying an initially modest warm anomaly into a considerably stronger event than the triggering wind burst alone would have produced on its own. Forecasters have specifically noted that when an El Niño develops this early and this rapidly, as this one clearly has, it frequently ends up considerably stronger by its eventual winter peak than initial forecasts suggested, precisely because early rapid intensification is often the clearest signal that this Bjerknes feedback loop has engaged particularly strongly and particularly early in the event's overall development cycle. I want to address something genuinely important about how confident scientists actually are in each specific layer of this now well-understood causal chain, because it's worth being precise about what's settled science versus what remains an active area of ongoing research. The basic physics connecting westerly wind bursts to El Niño development is genuinely well established. Decades of oceanographic research have confirmed this mechanism repeatedly across multiple historical events, and it represents settled foundational understanding within the broader field of ENSO science. The specific attribution of this year's triggering wind burst to the triple cyclone cluster near Papua New Guinea, while genuinely well supported by the observed timing and location of both the storms and the subsequent wind anomaly, represents a more specific, case-by-case causal attribution, exactly the kind of detailed forensic analysis that becomes possible once researchers have the benefit of examining a specific, already unfolding event in real time, rather than working purely from generalized historical statistics, and the ultimate question of exactly how strong this event will become at its eventual peak, while now carrying genuinely high confidence toward the very strong category given Roundy's statistical analysis, still carries some genuine uncertainty regarding whether it specifically breaks the all-time record set by 1997-98, a distinction that will only be fully resolved once this event actually reaches and passes through its winter peak. Let's talk about what all of this actually means for the world, because a historic El Niño of this scale carries genuinely global consequences, reaching far beyond just the ocean basin where it originates. The impacts of El Niño are felt the world over, from diminished fish stocks off the coast of Peru as the warm water suppresses the nutrient rich upwelling that normally sustains that region's fisheries, to the suppression of monsoons and rainfall across India, China, and much of Southeast Asia, regions where hundreds of millions of people depend directly on reliable monsoon rainfall for agriculture and water supply. Barely a corner of the planet is left unchanged by an event of this magnitude, and Roundy specifically noted a pattern worth understanding directly, that normally wet places become dry and suffer fires, while other regions experience the exact opposite shift toward unusually heavy rainfall and flooding, depending on their specific geographic relationship to the reorganized atmospheric circulation this kind of event produces. Here in North America specifically, the same mechanism is already reshaping the outlook for the season ahead. A strong El Niño historically shifts the winter storm track southward and strengthens the subtropical jet stream, raising the probability of wetter conditions across California, the southern plains, the Gulf Coast, and the southeast, while the northern tier of the country often trends milder and, in some regions, drier or less snowy overall. The World Meteorological Organization has placed an 86% probability on at least 1 year between 2026 and 2030, breaking the current global temperature record, a statement reflecting both the ongoing baseline warming trend and the specific additional boost a genuine super El Niño event of this magnitude tends to contribute on top of that trend. Climate scientist Daniel Swain has described this mechanism directly, explaining that a strong El Niño event releases stored ocean heat directly into the atmosphere, producing what he's called a mini, temporary, but genuinely natural boost to global temperatures on the order of a 0.2 to 0.3 degrees Celsius, layered directly on top of the underlying longer-term human-caused warming trend. And Swain expects 2026, 2027, or potentially both years, to set new global temperature records specifically because of this compounding effect. So let's bring this entire story together into the actual, complete answer to the question this video set out to answer. Scientists didn't just notice a super El Niño was forming this year, they traced the specific mechanism behind why it formed with such unusual speed and unusual strength. Back to an E. Extraordinarily powerful series of westerly wind bursts, themselves apparently amplified by an unusual cluster of 3 simultaneous tropical cyclones near Papua New Guinea that pushed a reservoir of warm Pacific water eastward with more force and more accumulated warmth than the equivalent event that preceded the historic 1997-98 Super El Niño. That finding, confirmed through detailed statistical analysis of 86 years of historical wind data, is exactly why researchers now describe a very strong El Niño as close to certain for this coming winter, with the specific question of an all-time record remaining the one genuinely open piece of this otherwise increasingly well-understood story. Well, if you want to actually follow this event as it continues developing, NOAA's Climate Prediction Center publishes updated ENSO diagnostic discussions on a regular monthly schedule, and researchers like Paul Roundy continue publishing detailed technical analysis of the underlying wind and ocean heat content data driving this event's continued evolution. I'll be tracking this historic El Niño closely as it continues strengthening toward its projected winter peak, watching specifically for whether it ultimately surpasses the 1997-98 event's record intensity, and I'll bring you a complete update the moment that question resolves one way or the other. Subscribe so you don't miss that update, and drop a comment below with your own reaction to learning that 3 simultaneous tropical cyclones near Papua New Guinea may have played a direct role in triggering one of the strongest El Niño events ever recorded. I read every one of these, and I think a discovery this specific, and this genuinely traceable back to a distinct atmospheric event, deserves real attention rather than getting lost in the broader, more generic seasonal forecast headlines. Stay curious about the science behind the weather patterns shaping this coming year, and I will see you in the next one.